Today we are going to talk about the collapsible soils. These are unsaturated soils that can withstand relatively large imposed stresses with small settlement at low in-situ moisture content, but will exhibit a decrease in volume and associated settlement which could be of large magnitude, with no increase in applied stress if wetting occurs. So please go through this statement again. These are unsaturated soils that can withstand relatively large imposed stresses with small settlement at low in-situ moisture content, but will exhibit a decrease in volume and associated settlement which could be of large magnitude with no increase in applied stress if wetting occurs. So basically we are having the open type structure, and you can see the particles are connected with each other and the water bridges are present. Occurrence in the world. Extensive deposits occur worldwide. Sensitive clays of Scandinavia and eastern Canada, large formations of China, Russia and eastern Belarus, red sands of the southern African east coast, residual soils such as Highveld granites of South Africa, Kalahari sands, the black cotton soils of northeastern Nigeria, Cameroon and Chad. So look at that. The granite, because of weathering, residual granite consisted of quartz, mica flakes and kaolinite. It is characterized by quartz grains embedded in some silt materials together with fine sand and colloidal matter. The rainfall will leach out the soluble colloidal material, leaving a honeycomb structure. That means the open structure. So this is a very important point. In dry environment, coupled with the little salts in place, the joints where the quartz grains meet, some moisture will be trapped, so the honeycomb structure can withstand some considerable force when dry, but when saturated, collapses and creates a host of collapsible soil problems. Characteristics of such soils: open structure, high void ratio, low dry density, high porosity, geologically young or recent altered deposits, high sensitivity, low interparticle bond strength. The behavior of collapse is illustrated below. Well, you can see the settlement along vertical axis and the time along horizontal axis and what is happening. So with the passage of time, you can see that when the soil is partially saturated, what is happening to the soil, the settlement, there is increase in the settlement. So look at that, normal settlement with soil partially saturated. So from this point to this, the soil is partially saturated. But what has happened over here? Look at that. Additional settlement with no change in applied pressure but increase in moisture content. So simply you can say it like that, you are having the partially saturated soil, we are increasing the load on that soil, so obviously there is an increase in the settlement. Up to this point, you are having this much settlement, but at this particular point, that soil now has been saturated. So obviously increase the moisture content, but there is no change in the applied pressure. What has happened over here? There is sudden collapse or sudden increase in the settlement values. So if you just look at this part, additional settlement with no change in applied pressure but increase in moisture content. So this is the typical behavior of collapsible soil. According to Dudley 1970 and Harden et al. 1973, four factors are needed to produce collapse in a soil structure. Number one, an open, partially unstable, unsaturated fabric, a high enough net total stress that will cause the structure to be metastable, a bonding or cementing agent that stabilizes the soil in the unsaturated condition, the addition of water to the soil which causes the bonding or cementing agent to be reduced, and the inter-aggregate or intergranular contacts to fail in shear, resulting in a reduction in total volume of soil mass. So collapsible behavior of compacted and cohesive soils depends on the percentage of fines, the initial water content, the initial dry density, and the energy and the process used in compaction. So these are the different factors which should be considered for the collapsible soils. Okay, why do we have problems with collapsible soil? Either one or all of the following problems may allow collapse to be evident in construction. Number one, construction was carried out before collapse phenomenon was identified. No geotechnical assessment was carried out. In case the geotechnical assessment was done, it did not evaluate correctly or identify potential collapsible soils within the profile. Recommendations given by the geological engineer was ignored by the parties involved in the design. Evaluation and prediction. For field identification, observational method, look for cracking and building distortion. Soil profiling, recognize a loose or open fabric. Use a hand lens to look for colloidal coatings and clay bridges. Sausage test. This is an interesting test. Carve out two cylindrical samples of undisturbed material to nearly as possible to same diameter and height. Wet and knead out sample and remold it to the same dimension you had. A decrease in height when compared with the undisturbed material is indicative of collapsed material. The laboratory testing which is required for such soils: particle size distribution, Atterberg limits, dry density, and consolidation test. So consolidation test, that is the most important test for such soils. Collapse potential test. So this is the main test which is to be done for such soils. The collapse potential test is a special case of single consolidometer test. Sample is saturated at a load of 200 kPa. So this is very important step. According to Jennings and Knight 1975, the collapse potential is not a design parameter but is an index figure providing the engineer with a guide to the collapse situation and whether there is a good reason for further investigation. The table below gives guidance to the severity of the collapse. So through collapse potential we can determine the collapse potential value, and based upon that value you can rate the collapsibility like that: no problem, moderate problem, problem, severe problem, very severe problem. So 0 to 1% no problem, 1 to 5 moderate problem is there, 5 to 10% problem is there, 10 to 20 severe problem, and when you are having more than 20% collapse potential, very severe problem. To understand that test, what we do now, in the consolidometer, the sample is placed at the natural moisture content, and you can see that the initial void ratio is E naught, and we are increasing the pressure upon that soil, and you can see with that there is decrease in the void ratio. But when you have got 200 kPa pressure upon the soil sample, then it is soaked or it is saturated, and you can see what has happened at this particular pressure when you are going to saturate your soil. So you can see there is sudden reduction in the void ratio delta E. When there is no further decrease, then you can increase the load, and you will be having this pattern, this type of the behavior of the soil. So the main thing is that at 200 kPa pressure, the soil is being saturated, and you can see that there is sudden change or sudden decrease in the void ratio. So as far as the collapse potential is concerned, it can be determined percentage by using this formula. So this decrease in void ratio that you are having at 200 kPa pressure divided by 1 plus E naught into 100, so this is called as the collapsible potential. So in this diagram you can see this is the void ratio. This axis is meant for the void ratio, and this is the log of pressure, and this is the 200 kPa pressure. Engineering solutions. Precluding the triggering mechanism, ensure that the water does not reach the collapsible soil horizon. Chemical stabilization. Stabilizing agent may increase the strength of colloidal bridges. Research on this area is limited. Use of sodium silicate and injection of carbon dioxide have been suggested. Then piled and pier foundations. Structural loads may be transferred through the collapsible soils by means of piled or pier foundations. This method is suitable for soils whose origin is transported. Then in that case the transported soil which is collapsible is shallow and underlain by stable soils or rock. Then design for the collapse as quantified. Increasing structural flexibility by the provision of joints or reducing the bearing pressure to restrict collapse settlement. Raft foundations are suitable for this case. Make sure there is no increase in moisture in the underlying soil with time. And then the next option is the option of the densification. The soil should be compacted to sufficient density such that collapsible potential is less than 1% down to the accepted depth of the influence. For road work, compact to 95% modified ASHTO for 0 to 0.5 meter and 85% ASHTO for 0.5 to 1 meter. This could be combined with removal and compaction. If you are having the poor soil, that can be removed and it can be replaced by a good material. Vibroflotation, dynamic compaction, in situ densification by surface rolling. Use impact and vibratory rollers to get more effectiveness. So that's all about the collapsible soil. Thank you.